For the last example in this lesson, we're going to take a look at a new class called Account, where we will introduce a couple of new features, including the concept of a decimal number, which is typically used for financial calculations or precise floating point arithmetic, as well as the concept of validating data in a class as well. And also just a new class to give us something different to look at from the gradebook class that we've been looking at for the first several examples. So here I've loaded up the project for the new example, and as in the format of our previous projects, we have one class, which is the class that we're really defining and testing, and then a separate class with the word test in it to play with the new class that we've created. So let's go ahead and take a look at our account class. Now the account class might be used for something like a bank account where you need to maintain a balance. So for the class account, what we've done is define the class account to have one instance variable called balance. You can see that it's a private instance variable and that its data type in this case is decimal. Now the only built-in type that we've talked about so far is the int type, which is one of the value types, as is decimal. So when you manipulate a decimal, the variable actually contains the value. It is not a reference to some other object in memory. Now, decimal is typically used for high precision floating point arithmetic, such as financial calculations. And one of the reasons for that is the other two types, float and double, that are typically used to represent floating point numbers are less precise than a decimal is. In a float, you typically have 4 bytes of memory to store the information and a maximum accurate precision of about 7 digits. For a double, you have 64 bits in which the value can be stored and about 15 to 16 digits of precision. And in the case of a decimal, it's stored in 128 bits of memory, so 16 bytes of memory, and has approximately 28 to 29 digits of precision, which is much more precise than the other floating point types. So for that reason, we've chosen to use type decimal to represent the balance of an account in this example. Now, for our account class, we provided a constructor. In general, just about every class you ever define is typically going to have at least one constructor, perhaps with the exception of classes like account test, where the only purpose of them is to define main to launch your program. But most classes will have constructors associated with them. In this case, we have a single constructor named account, which is of course the same name as the class, a requirement for constructors. It is declared public so that we can use it from other classes, such as the account test class that we'll use momentarily. And this constructor expects to receive a decimal called initial balance as its argument. And what it's simply going to do is take that initial balance and assign it to the property named balance, which you can see I define starting at line 22. Now, one indication that this is a property as opposed to an instance variable is the fact that it has a capital B at the beginning of its name. Instance variables normally start with lowercase first letters, whereas properties and method names and class names typically start with capital first letters. Now, the balance property has a set accessor, which will be invoked when this equal sign is executed, and that set accessor will receive the initial balance and assign it to the instance variable called balance. Now, I'm going to actually take a look right away at that property definition down towards the bottom of the class here so that we can see what that set accessor looks like. So here is our property, and in this case we chose not to use an auto-implemented property because we wanted to do some validation in our set accessor. If you have any logic at all that you need to build into your get or set or both accessors, you must define a traditional property as opposed to an auto-implemented property. So that means it becomes our responsibility to provide the instance variable that's going to be manipulated, and then our responsibility to define the property for manipulating that instance variable. So you can see our get accessor, is very straightforward. All it defines is to return the current value of the balance instance variable. And if I hover over that, we can see that's the decimal called balance in class account. And then separately, we have this set accessor. And for the purpose of this example, we want to make sure that we never assign a negative value to the balance. So we're doing a simple bit of validation here to ensure that the value being assigned to the balance piece of data is always greater than or equal to 0. If it is, then we take the value that was passed into the set accessor and simply assign it to the balance. Otherwise, we leave the original balance alone. So if, for example, I were assigning a negative number to the balance after I go ahead and create an account object, then the set accessor will simply ignore that operation in this case. Now, that's probably not the best way to handle that logic error of assigning an invalid value. What we could do is instead throw an exception, which is something that we'll introduce in later lessons, so that the caller of the property, the code that's actually using the balance property, knows that something went wrong and can attempt to resolve that problem. So that's our balance property. And in addition to the balance property, we also have a credit method, which is simply going to credit an additional amount to the balance by adding that amount to the balance. Now you can see here that we're using the balance property on both sides of the assignment. And we certainly could also write that as balance plus equals amount, which is the plus equals operator, which is shorthand for doing the statement that's shown here on line 18. And both of these statements simply add the amount to the balance and store the result in the balance property, which in turn, of course, is placing its value into the balance instance variable of the class back at line 7. So that is our account class. And again, we're trying to model a real-world concept of an account. So for that purpose, we have the data that stores the attributes of an account, in this case just the balance, but of course a real account would probably have a person's name and some sort of identifier and other information associated with it. That's something for later lessons. We have a constructor to initialize the balance, a credit method to manipulate the balance by adding an amount to it, and certainly we could consider a debit method as well. And finally, that property for manipulating the balance to both get it and change its value. So let's go ahead and test that class. And for that purpose, we have an account test class. Let's go ahead and run this first so you can see the results on the screen here. And I'll come back and look at this as we go through the code, and I'll enter a deposit amount at that point. So here at lines 10 and 11, we've created two account objects. The variable account1 stores a reference to an account, and it specifically stores a reference to the account that has the initial balance of 50, and the M that you see here indicates that 50 is a decimal literal value. When you don't put the M indicator at the end of the literal value and it's a floating point number, the compiler automatically treats it as type double. So because we're dealing with decimals and not doubles, we hard-coded the M here to indicate that 50 is a decimal literal, not a double literal. And by the way, in all of the C-based languages, when you have a floating point literal in the code, they all treat that as a double by default. At line 11, we create a second account object called account2, also of type account, and it's going to refer to the new account object that we are attempting to initialize with a negative value. Now, I'm going to run this again in the debugger in a few moments, and when I do, you're going to see that the balance property is simply going to ignore that negative value. So just before we do that, let's go back and look at the source code, and we can see that the constructor assigns a value to the balance property. That's going to invoke the set accessor of the balance property. The set accessor says if that value is greater than or equal to 0, then assign it, otherwise don't. And if you look at the output so far, you can see that account 2's balance is 0. And the reason for that is the instance variable rather, named balance, is set to 0 by default. And the constructor is now in the process of trying to change that value to whatever value is passed in as an argument as the initial balance. And if that value is invalid, then we simply don't allow the data to be assigned in this example. And that's an example of keeping the data inside the object in a consistent state, a state that's consistent with the use of that object. It doesn't mean that the data is valid because, of course, we gave it an invalid value in the first place. And this is, again, where exception handling can come in handy. So we've already seen the validation in action here. The next thing we did was to display the balance of each account, and for the first time we're using some formatting in our format placeholders here. So account 1's balance is going to be placed in this curly braced location. 0 is the argument number, the first argument after the format string, account1.balance, and :C indicates that we want this to be displayed in currency format. So if I go back to the output again, you can see because I'm in the United States locale that it's showing me that currency as $50, whereas if you're executing this in a different locale, you may see that displayed as 50 euros, for example. And similarly, account 2's balance is also displayed in dollars and cents. So you can see in both cases that we specified a format for the data that was being displayed, and at the end of this example I'll take a look at a table that shows you some of the other format specifiers. So the next step is going to be for us to complete the input that you saw the program waiting for. So you can see it's expecting me to enter a deposit amount for account 1. So going back to the code for a moment, first we declare a local variable called deposit amount of type decimal. Now, a local variable like this is not initialized when you declare it unless you explicitly place an equal sign and a value to the right of the variable name. So I must initialize every variable before I attempt to use it. For instance variables, if you don't explicitly initialize them, they are implicitly initialized to their default values. For local variables, there is no default initialization. So here at line 22, we prompt the user for the amount to deposit. We then read in that amount, and we showed you a similar statement back in the first coding lesson where we read in a line of text containing a value, and we converted it in that lesson to an integer value. Here we're converting to a decimal value whatever string is input by the user. Now that means I'm assuming once again that the user will type a proper decimal value. If I were to type hello here, then the program's going to fail at this point with an exception as I demonstrated to you previously. So going back over here, let's say we want to add to the first account balance 1.23, so $1.23. When I press enter, it says that it's doing that addition, and then you can see my new updated account 1 balance. Notice once again that it did not modify the account 2's balance, and that's because each individual object maintains its own balance. And you can see down here when I called credit, it was called on the account 1 object with that deposited amount. And because we called it specifically on account 1, only that balance gets modified. So the next thing we did was to display the new account balances, which you just saw on the screen. And then just to demonstrate that we can modify the balance for account 2 as well, these lines are going to prompt the user to enter another decimal value. We then read that value in and display it, and finally credit that to the account 2 object in this case. So now if we go over to the output window and let's type 123.45 for the credit to account 2, we can see that only account 2's balance gets modified in this case. And as I promised, I do want to go back and run this in the debugger as well. So I just want to show you that the two different accounts are in fact being initialized, and more importantly that when account 2 gets initialized, that we are skipping the value minus 7.53 because of the validation that's occurring. So I'll set my breakpoint on line 11 here. So at this point we can already hover over account 1 and see within the tooltip here that the balance is 50. On the other hand, account 2 is currently listed as null because it has not yet been initialized, and we're about to do that. So I'm going to step into the constructor, and you can see as we step into the constructor that we're going to have to execute the assignment statement, balance is assigned initial balance. This is going to invoke the property, and again, if I haven't disabled this capability of stepping over properties and operators, then it's going to simply step right over this. When I try to step into it, I previously disabled this capability, and I did that just by right-clicking on the property. So let's go ahead and step in now to the balance property, and now we're going to execute the set accessor, and we can see right now value is negative. Therefore, this condition is going to fail, and we're going to skip over line 33. So I'll go ahead and execute that, and as I do the step over to evaluate this condition, you can see that it jumps right to the end of the set accessor and back into the constructor, and then after the constructor completes, back into main. And now we can look, whoops, let's step one more line. Now we can look at account 2, and we can see that the balance is 0, even though we tried to set it to minus 7.53. So clearly we can see down here in the debugger the two separate account objects with their two separate balances. And similarly, if I go down, let's set another breakpoint here at line 29 and continue to that point in the code. So it's going to ask me to enter a deposit amount, so I'll go ahead and do that. And now we can clearly see down here in the debugger that only one of the two account balances got modified, and notice by the way that it displays the modifications in red within the locals window. So in this example, we got a chance to show you a new class and introduce the concept of decimal data in .NET. We also showed you a little bit of validation in a set accessor, which gives you a little more information about why it's useful to have a property. By having a private piece of data in the class, an instance variable, and a public property, we were able to prevent the client code, my account test class, from placing an invalid value into an account object when we first created it. And similarly, if we had simply assigned a bad value to the balance, that too would have prevented a negative number from being applied. And in later examples and later lessons, we'll start to get into exception handling to demonstrate other ways to deal with such validation errors. So the last thing we want to look at for this example is just a table of some of the other format specifiers that are available to you when you're using things like console.writeline statements. So we showed you in this example that you could display things in currency format by using the format specifier C. You can also use a lowercase c as well. And you can see that there's a number of additional formats as well. So for example, D is for integers, N is for numbers that are displayed with thousands separators and also provide for 2 digits to the right of the decimal point by default. E is if you would like scientific notation. F is for floating point numbers with a fixed number of digits to the right of the decimal point, so 2 digits by default, and we'll use that actually in the next lesson. G is actually going to decide between using the exponential scientific notation or just a fixed point notation based on the magnitude of the value. And then finally, X is used to represent hexadecimal notation as well. And all of these are explained in the online documentation. So if you look at the overload of the WriteLine method that expects as its first argument a format string, it will refer you to the documentation where all of these format specifiers and the additional formatting capabilities are defined. Not only can you do this in the context of a WriteLine statement or a write statement that's going to output to the command prompt, you can also just do this for string formatting in general. So much of this comes from the string class.